This is the last section of chapter 2 on graphs and networks, and this is the planarity algorithm. Now, this algorithm is going to help us solve these types of problems. Now, let's say we've got 3 houses and we need to connect all 3 houses with gas, electricity and water, but the cables or lines or pipes that we use mustn't cross each other. Now, I could go around any direction to join a utility to the house. Let's say, for example, I do gas like this and join that to the houses, so none of those paths are crossing, like this. And then let's say I go to the electricity and put some electricity here and some electricity there and some electricity here, and then I come and do the water. So let's say I connect the water there and I connect the water to there. Now I'm going to run into a problem because this line is not allowed, or these pipes here, or wires are not allowed to cross. Now I've just done it by trial and error, but we can actually use an algorithm to find a solution, if there is a solution to this problem. And the solution is all about whether, if I draw this as a graph, whether that graph is planar. Now, a planar graph is one where the edges of that graph only meet at a vertex. Now, these two graphs here are essentially the same. They've got the same number of edges, the same vertices are joined together, but one is not planar and the other is. So the first graph here is not planar, and the reason it's not planar is because we have edges crossing at a point which is not a vertex, which is here. Yeah, those edges cross each other, they meet each other at a point that's not a vertex, so it's not planar. However, by taking one of the edges, if I take this edge here and draw it around the outside, like this, the edge that goes from A to D, this graph now becomes planar. This is now a planar graph. The edges only meet on this graph here at a vertex. So the algorithm we're going to go through now describes how we can take a non-planar graph and see whether it can be drawn as a planar graph. Not all graphs can be, but we've got an algorithm to see, to actually work through how we do that. Okay, now here's the algorithm. It will make more sense when we do an example, but I'll just run through it. So the first thing that we need to do is, with our graph that's given, we need to find a Hamiltonian cycle. And remember, that's a cycle that visits every vertex. So we need to find that cycle. Once we've done that, we need to draw this cycle as a polygon. So depending on how many vertices we've got in our original question, maybe 8 or 9, it's going to be some sort of octagon or polygon. And we need to ensure that it is labeled correctly in the same order as our Hamiltonian cycle. Third step, we need to add in any other edges from the original graph, because we're not going to have all the edges in this polygon. We're just going to have our cycle. So any other edges that are from the original graph, we draw these inside the polygon. Then we need to list all of these edges that we've drawn inside the polygon. Now, it may be useful at this point actually to have all the edges listed at the start. Now, this is the way I'm going to do it. I'm going to list all the edges here, just modify this slightly, and then you'll find it's helpful when we get to this stage. Step number 5, we want to choose any edge on the list. That's basically any edge that's inside the polygon, and we're going to label it I for inside. Then we're going to look for any unlabeled edges that cross I. So this edge that we've just identified, we've picked as I, we're going to look for edges that cross it. Now, if these edges that cross I, if they cross each other, then the graph is not planar. It cannot be drawn where edges only meet at a vertex. Okay, if the lines don't cross, that cross this edge I, we're going to label them O. Then what we do, we'll repeat this step 5 for any unlabeled edges, and we'll repeat until all the edges are labeled. And then basically what this tells us now, that I is going to tell us that these edges we're going to draw inside of our polygon, and the edges we've labelled O, we're going to draw outside of the polygon like this. So this would be like an inside edge, that would be an outside edge, and that completes the algorithm. And for a graph that can be drawn as a planar graph, this algorithm will find a solution. Remember, these types of questions, there's often more than one correct solution. Okay, so we're going to use the planarity algorithm to determine whether this graph is planar. So the first thing I'm going to do is I'm going to list all the edges in this graph, and this list of edges is what I'm going to use when I get to step 4 and 5. Right, so here's a list of all the edges. Okay, now to ensure that I haven't missed any edges off, I'm just going to highlight them as I go along. So I've got AB, AE, AF, AH, that's the ones all begin with A, I've got them in alphabetical order, BD, BE, BH, then moving to C, so CF, CG, CH, then DE, DH, EF, FG, and GH. So it looks like I've got all of the vertices written down, or all of the edges written down. Now, this is before I do step number 1. So step number 1 is going to be to identify a Hamiltonian cycle. In other words, I want to find a cycle where I meet every vertex and I want to start and finish at the same place. Remember, that's the definition of a cycle. Okay, so here's a Hamiltonian cycle. There's more than one, but just to show you, this visits every vertex, and maybe I'll highlight as we go along. So we go from B to D, D to E, E to F, F to C, C to G, G to H to A, and A to B. So there we go. That is a cycle that meets every vertex. So the next thing we're going to do is to draw this as a polygon. So since this cycle is a cycle of 8 vertices, we're going to have an octagon, and we'll label it in the same order as our cycle. So we'll do B, D, E, F, C, G, H, A, and then back to B again. Okay, now this needs to match our original graph here, so we need to add in any extra edges that are missing in here from the original one. Now this is where our list here helps. So what I'm going to do, from this list, I'm going to cross off all the edges of this polygon. So I've got BD, DE, EF, FC or CF, GC, GH, AH or HA, and then AB. Okay, so now I've got a list of the other edges that are here but not in this polygon. So all I need to do now is to add these edges into my diagram. Okay, so I've now added those edges in, so they're basically just the ones that I haven't crossed out. Now I move on to the next step of the algorithm, which basically says, now pick any of these edges in my list. I've already got these edges in here listed because I did it right at the start, crossed out the ones which make the outside of the polygon. So I don't need to list them, they're already here. It's a little bit of an advantage of doing it this way. So I can pick any of the edges from this list. Now I'm going to pick, I'll pick this one here, FG, and whichever one you pick, you call it I. And I stands for inside. So my edge, FG, I'll highlight that, is this one here. I'm looking for any edges that cross FG, and the only edge that crosses FG is this one, CH. Okay, if there were multiple ones that cross this, I look to see whether those edges cross each other, but there's only one edge that crosses it, that is CH, so we label that O. for outside. So I'll just put an O there for CH. Okay, so now I'm going to pick another edge from my list that hasn't been labeled up yet. So I'm now going to pick DH, and DH is this edge here. So let's just highlight that. There's DH. And what I'm looking for edges that cross DH. Now I can see there are 3 edges that cross DH. Do any of these edges that cross DH, do they cross each other? No, they don't. They meet, but they don't cross. Okay, if they did cross, then the graph is not planar. I would just stop. But I can see these 3 edges, they don't cross each other. So I label these edges as O. So that's BE, I label as O for outside. And then AE, I label as O for outside. And AF, I label as O for outside. And then I carry the algorithm on. So I'm now looking for another edge from my list. I need to label this inside because that was the one I just picked. Any edges from my list that I haven't yet labeled, and the only one I haven't labeled is BH. So let's label up BH, which is here. Now I can see there are edges that cross BH, but they need to be unlabeled edges. Are there any unlabeled edges that cross BH? Well, there aren't, because AE and AF are already labeled. So we'll just label BH as I for inside. There's nothing to label as outside because the edges have already been labeled. So now, since all edges are labeled, we can say that the graph is planar. So we must state that. So we'll say, since all the edges have been labeled, the graph is planar. Now the best way to check that is to draw it. Okay, so I'm going to draw this octagon again, and basically all these ones that say I, I'm going to draw on the inside, and all the ones that say O, I'm going to draw on the outside. Is certainly going to be loops that go around the outside. Okay, so here's my original Hamiltonian cycle, and let's add these edges in. I'll do the inside ones first. I'll do BH. It's going to go inside like this. So we've done that. Then DH is also going to go inside, so we'll tick that one off. And FG is the only other one that goes inside, like this. We'll tick that off. Now all the other ones go outside of the polygon. So A to E is going to go around like this. Then A to F, which we can do without them crossing, because it can go around like this. We could even go the other way. So I'll tick that off. Then B to E. So B to E, that's fine. It's not going to cross because it's going to go there. And then last of all, C to H, and C to H, that's going to go around the outside there. So you can see what we've got now is a planar graph. The only place where the edges meet is at a vertex. Now this is just one solution. Okay, now if I identify a different Hamiltonian cycle at the start, I'm going to get maybe a different solution to this one, but this proves that it works. I've got all the original edges that were in the original diagram, but I've redrawn it so that none of the edges cross. They only ever meet at a vertex. Right, so we've got an electronics company that attaches components, 6 components to a circuit board. These components are to be connected by wires that are not allowed to cross. So when I see that, I should be thinking to myself, right, is this a planar graph where maybe the wires equal the edges and the components equal the vertices? And this table gives information about the connections here. Using this Hamiltonian cycle, so they give us a Hamiltonian cycle, we don't need to find one, apply the planarity algorithm to determine whether the connections can be made without any wires crossing. So the first thing I'm going to do is to make a list of the wires or connections, which is basically a list of the edges. Okay, so these are all the edges listed. So I'm now going to draw the Hamiltonian cycle, which is 6 vertices A, B, C, D, E, F. Join the edges and then cross off these edges from my list, and then the remaining edges are going to go inside. So we'll cross off A to B, B to C, C to D, D to E, E to F, and F to A. So the remaining edges I'm now going to draw on the inside. Okay, so I've added the extra edges in there. So let's start with just like the first edge on the list, AD. Let's highlight AD to see what edges cross it. So there's AD. So I can see that these edges cross BF, BE, and CE, and these edges here do not cross each other. So I can label those ones the opposite, so O. So BE, BF, and CE as O. So let's change that I, that should be an O. Okay, then the next thing we're going to do is to pick the next edge on the list. And that next edge is a E. We'll label that as I. So we'll highlight edge AE, like this. Okay, now if we carry on, what I'm going to do, I'm going to highlight the edges to highlight a problem. Now whenever we do this algorithm, any edge that we label as I, which I've actually highlighted as green, so that will be like an inside edge. Any edges that cross it should only be edges which are labelled as O. Okay, we can't have edges which are inside crossing inside edges, or I edges crossing I edges, or outside edges crossing outside edges. Yeah, so this one, AE, we've got to this point here, we've decided to label this one as I for inside. Okay, so the edges that cross it can only be O edges. Well, BF, that's fine, because we'd already labelled BF as an outside edge. So I'll just highlight that in orange. There's an outside edge there. Now it also means I'd have to label DF as an outside edge. Yeah, so that doesn't seem like a problem. So let's label that as outside. You might think, well, we'll just go on to BD and we're finished. But let's look at the edges which cross DF. Now, what edges cross DF? Well, BE crosses DF, and we've already labelled BF as an outside edge. So there's an issue here, an outside edge crossing an outside edge. And we've also labelled CE, which is the other edge crossing DF, and we've already labelled that as an outside edge. So again, we have this problem here where we've got outside edges crossing a label that we want to, or an edge we want to label as an outside edge. Now, you may not necessarily spot this issue until you actually come to draw it and then realize you're going to have edges that cross each other. So what we're going to do, we're just going to put that explanation in words. So we could write, if we label DF as O, which is what we want to do because we've labelled AE as I, it will then cross, DF will then cross two edges, BE and CE, that have already been labelled as O. This will mean that these outside edges would cross. So if we've got outside edges crossing in our algorithm, we'll have outside edges crossing in our answer when we try and draw the graph. If we had inside edges crossing in our algorithm, we would have inside edges crossing in our graph if we try to draw a planar graph. So yeah, this would mean the outside edges would cross, meaning the graph is not planar. Okay, so you should now be able to do exercise 2E on pages 46 to 47. So this is just a list of the steps that you take when you apply this planetary algorithm. Just a couple of notes. You may find it useful to list all of the edges first and then cross out the edges in a Hamiltonian cycle, which may be given. They may give you the Hamiltonian cycle in the question. And also a way of checking whether a graph is planar or not. There's two ways. One, if the edges that you check for crossing I, if they cross each other, then it's not planar. Also, if you've got I edges crossing I edges, or O edges crossing O edges, then also the graph is not planar, because that would mean if you try to draw the graph, the I inside edges would cross, the ones that cross in the algorithm, or the outside edges would cross those that cross in the algorithm.